Okay, so another thing so in terms of optimizations, let me go back here, user's guide. Let's see what other options we can have for the optimizations. Okay, so if you go to, let's say, optimize here, this is the keyword section. We actually use two different programs to optimize. This is the default. The Sci-Fi is the standard optimizer, not just optimizer, but lots of scientific calculations. It's a Python library. We use this, but there is another one, which is DLFind. There is a Python wrapper of DLFind. We use DLFind. Right now, this is the default. There's an advantage and disadvantage of each of these. If you want to do more sophisticated optimizations, like notched elastic band path, which we haven't implemented it, but we are going to notched elastic band path optimizations. We have to use the DLFind. In that case, live equal to DLFind. Right, then there is a DLFind section here. Then we need to specify the options here, and then so lots of options. So this is a bit involved, but I think that all we need is the good input examples, right? So we will. Once you have input examples, you could do all this calculation. Now, let me go to another file while this is optimizing. CI21, meaning that the conical intersection between state 2 and state 1. How does it look like? Well, we use the same input XYZ, or you can use S1 optimized geometry, or S0 optimized geometry, but or another geometry you need. Runtime is MECI, meaning the minimum energy conical intersection search. And then most of them, the only thing that you need to really careful about is these two part. So now you need the two states, right? So that's why you are optimizing two states to get the touching point. So that's why it says I and J state. That's why we use I state here. So you specify 2 and J state is 3. So meaning that state 1 and state 2. And then what it does is that if you specify this, is that not only the gradient of state 2, we also compute gradient of state 3. And using those information, the algorithm is trying to locate conical sections. And so we can play with this. In fact, we found that there are many conical intersection that has more than 2 states crossing, 3 state crossing also possible, 3 and higher. And so we will eventually implement those too. But right now, you can locate 2 states. So this is very simple, right? You just change a few keywords and just run it. And then also you can do the Hessian calculation. Let me go back here. What other calculation? Yeah, sorry.
The conical intersection can be more than 2 for 2 states. Like, let's say state 2 and 3, there could be more than 2 conical intersections. And which one this program would find it? Or can you find more than 2?
Conical section can be a lot more than 1, as you know. And so what state we are finding is strongly depends on the initial geometry.
Right.
So if you start with the Frank-Condon geometry, it will find the one that is closest to the Frank-Condon. But one of the way we find the conic section is that it's a very difficult to find because it's a very difficult to guess the what structure it actually is. So without thinking, you can just use Frank-Condon geometry because then you can find something. And then we do the trajectory calculation, non-adiabatic trajectory calculations, so that we will see whether the hopping occurs. So at that hopping point, we collect those geometry and then we start new conic section search from that geometry. Then we can find another conic sections. So normally it is almost impossible to guess the possible structure of a conic section. Therefore, we do something like this. Maybe my student knows better than I do. But once we study the structure of a conic section, eventually maybe we can come up with a good initial guess for that. For example, especially conic section between ground and first excited state usually has sp3 hybridized from S2 to sp3 hybridized structures. So normally benzene has a planar, right? But one of the bond is kind of out of plan twisted, bented. Then it creates the sp3 carbon at that carbon. So, but that's just the one possible structures. So there will be a lot more conic sections. But another point would be that we don't need to find out all the conic sections that is possible because there are so many out there. We need to find the conic section that is near to the energetically similar or slightly lower. If it's too high, then we probably don't need to find those. So that's why we probably need to perform some trajectory calculations, including non-adiabatic the transitions. Then once we observe some hoppings, then we just use those geometry. That is the kind of strategy we usually do.